Hi, am I audible or? Hello? Hello, am I audible or is there any problem?
You are audible.
Okay.
Would you like to get recorded and after uploaded? Should we upload your talk? How have you prepared?
Yeah. I think that's okay.
Otherwise, you can just share the slides afterwards and we can post it.
Okay, fine. I just share the screen. So.
Did you ask Hasnanji sir?
Yeah. Yeah.
He will join.
Yeah. He will join. Are you seeing the slides?
Yeah, visible.
Okay.
So I was reading a fact yesterday. It looked me a little surprising. Let me tell you.
What? Are you saying something?
Fact was like if we have a regular tessellation, then a corresponding subgroup would be torsion-free of triangle group. Do you get my point?
Say again.
If we have a regular tessellation,
Yeah.
then the corresponding group would be torsion-free in the triangle group, some triangle group.
Actually, for trying, if you write any PQ pattern, regular tessellation, that's mean PQ pattern tessellation, right? So for
Your
PQ pattern
voice
tessellation,
actually, you see, your voice is bit not clear actually, right? What it called?
now
It is not
now
sharp actually, not sharp. Okay. Hello.
it's okay.
Like you are speaking under some plot.
Now it's okay.
It's better now.
Okay. So for regular tessellation, we'll get the triangle group that PQ2. So I mean, yes, regular actually in this triangle group, you just write like this. Okay. It's PQ times, I think, this tessellation. Is that okay or?
Okay. Okay, I think you can start formally.
So, okay. So I'm presenting the torsion-free subgroup for the triangle groups. That okay. So I part some elements of it.
माहित नाही आता किती वेळ चालू.
Hello. I want saying something? Or?
No.
Okay. So so first we see these are some basic things. So I'm gonna skip these things that definitions like there's a definition of fusion groups there, which is discrete subgroup of PCL2R, and it is finitely generated and presented like this. Hello.
Yeah.
Okay. So it is presented like this. We told G is genus and R curves. Oh, sorry, R elliptic parts and S cusps. Okay. So from the non-Euclidean area, we can see this into 2 by pi is the area of if we quotient out this the upper half plane by gamma, then we get a area of it. So obviously this is area, so it is positive. So and conversely, I know if we take S equals to 0, so then this will be, if this is positive, then there's a theorem by Poincare said that we get a Fusion group with this signature. Actually, these are called signature. If you write like this, okay, that's okay. Or
Yeah.
okay. So and another thing that the finitely generated fusion group contains a torsion-free subgroup. Actually, this is a known result. This is actually coming from the Selberg's lemma, which is actually saying that for any linear group, finitely generated linear group, then there is a torsion-free subgroup of finite index. Okay. So another thing is known to all of us, I think, the triangle groups. The triangle groups, actually, I'm taking this triangle orientation preserving triangle groups, which is index 2 part of it. Okay. So this, which presented like this. So actually, the generalization is falling from this. What?
UVW or what?
Actually UVW, you can say U is like YZ and okay, I think there is some typo. Hello. Yeah, sorry, U is XY and V is YZ and W is ZX. Then is that okay?
Okay.
Yeah. So it says something generalization. We can write this thing in generalization form that it is called D group, that every that U is like x1, V is like x2, something like that. So the D group is presented like this. And actually, in particular case, this is the fusion group with
What
zero
is-
genus and zero
What
carbs.
is UVW? Can you tell? UVW is equal to 1. Is it? Okay, okay.
Yeah, it's okay. Yeah, it's one.
Yeah, okay.
Yeah. So our main focus will be the finite index of the subgroup of triangle group. Means, actually, for this index, we actually got some information that about that if it is okay, it is even type or odd type something. You'll see. We'll see it later. Then, so I need some definitions like what is odd type. In the presentation of gamma, if the cast is 0 and the lambda is actually LCM of MIs, all MIs is even. If S is 0 and lambda is even, and lambda by mi is odd for exactly odd number of mi's, then then we can say gamma has even type. Otherwise, odd type, and otherwise we'll say gamma has even type. Okay, so again, this is fundamental thing, actually the fundamental domain. So I can skip it. Okay, yeah, and this is more into I think this is another interesting theorem, that we consider this positive integers, that mi's and re and vi's, then we can put just some conditions, that 2 equals to r into r, and 2mi vi equal to r, and the Euler characteristics condition. Then there exists a tessellation of m into r argon with e edges and summation vi's vertices. But actually I'll explain what are they actually. So here this is I can just tell the justification what is that it will create a tessellation. You can see this is r argon, right? This is r and argon. So so there will be r phase. Actually, the every simply connected part of the tessellation we called as a phase. So r argon, that means every r has r edges, and every edge counted twice, because every edge will part of two phase. So r into r equals to 2e, and we know that actually I add the example of it. So yeah, and vi is the collection, is the summation of is the number of all vertices which has a valence to mi. Actually, and if you can see, this will be the number of faces. Okay. So actually here in the particular case will be the PQ pattern. PQ pattern means you just take every valence as are same in each vertex, that all mi's are same, then it will be as PQ pattern. Okay, so I have some picture of PQ pattern. That PQ pattern actually you can say it's actually 3,
Okay.
2, 3, 7, or it's 4, 5. So if you can see the the 7 gone will the 7 gone is added for every vertex. Each vertex there will be 3 7 gone. Right. So PQ pattern say that that each vertex has valence 7. Okay. Similarly, it will happen also here, and this is an example of what I'm saying. This sorry, 2M1, 2M2, 2M thing. Okay, and the last picture, this is actually the triangle group of infinity, infinity, and infinity. So is that okay? Or hello? Hello?
Okay, yes.
Yeah. So the another thing is G branch covering. So G is actually group branch covering. So the N, we take the N as a closed surface, and B is a subset of N, which is discrete and finite. So yeah, fine. And G is be a finite group. So we just take a surjective homomorphism. We just consider it, and after that, actually this determines the covering map of this. Why? From this we get the kernel of the, and it is normal of this group. So actually this is star, sorry, okay, so this is a normal subgroup of and we all know that
What is your M naught?
M naught, actually the M naught, the space. I'm just connecting these two things, this and this.
No, what is M naught? I mean, what do you mean by, I mean, what is the notation? I mean, M naught means
M naught, okay. So
what kind of space? Reversal?
No, it's actually covering that if you write like this kernel, just like you say kernel is H, so H is a normal subgroup of this. So for every and we know for every subgroup we'll get a covering map. That covering map which
We can say something about M0 also, that cover genus or something.
Yeah, actually wait a minute.
So how do you construct this M naught? Just give me some idea. I mean, given such a subjective
actually M naught is like I would say like rather than normal cover actually.
Yeah, it is.
So it's the covering corresponding to this kernel.
Okay.
Yeah, yeah. Actually, that image will be the kernel of it, the image of M0, and M0 actually a covering space of this n minus b.
Okay, go ahead.
Okay. Okay. So this is yeah. So actually after and we just extend this M0 by this this option, that we just get this deleted neighborhood of a point of b in n, and just put the inverse of it and get a one punctured open disk. Sorry, a collection of once punctured open disks, distinct collection of, and so we just compactify the M0, and we'll call it M. So the phi 0 is extended up to 5, which is, and the phi is called G branch covering over n. Okay. And the and then for every x, the number of points in x0 is called branching index. We can denote it by nx. Okay. So for actually yeah, and for every this type of branch covering, the gamma is the Fuchsian group, which we see in the first section. Okay, and the pattern is actually a graph in n. Graph means if it is n, then if we want to test if we want to tessellate it, so it's actually tessellated by some graph. So this graph is called
In
okay.
theorem, your G was finite group, right? Now gamma is again a Fuchsian group here, right?
Okay. I think it is finitely generated, or there's a typo, I think, because otherwise it has no meaning actually. Okay.
So you want to say that for G branch covering, you can lift the pattern on the from targeted space to
Actually, the pattern will this.
Yeah, I understand pattern. I think you defined previously, right?
Yeah. Huh?
You already defined pattern in the initial slides, right?
Yeah. Yeah. No. It's PQ pattern is actually, yeah. These are like same thing. I actually just remind that give the reminder that K is what. Okay. Is that okay, or
Okay, you just confirm later that what is your G was.
okay. Okay. So this actually the phi inverse K is also a pattern of M. So phi. So yeah, and the valence will be, if we consider that this is every value for a point X, the valence will be Q. Then for points of X, phi inverse X, the valence will be NXQ, where NX is the branching index. So the two important lemma, actually these are for the case of PQ patterns. So the first lemma is the NBA closed and orientable surface, and B is just finite set. Then the then okay. So then there is a orientable GN branched covering of N if R is even or R is greater than 3 and N is odd, in which each branch point has an index N. It's for orientable case, and similarly the non-orientable case, for the non-orientable case, the R is even, is that R is even, then we got non-orientable Zn branch covering. If R is odd, sorry, N is odd, and I think R is greater than 1, then there is a Zn branch covering of non-orientable. Okay. So I think we don't need this gamma, that Fuchsian group. We just consider it like any finite group. Actually, this is more this is a better thing, I think. Okay.
So what happened? You are replacing gamma by G. I mean, that was your initial notation or something like that.
Yes, sir. See,
So G, I don't know. So you write gamma branch covering, no?
gamma.
So what is this group gamma?
Actually, this is you can say typo, because
Okay.
you can consider this as a finite group, because that's all we need right now.
So what was the initial G? Since I came a bit late, what was your G to begin with? It was a Fuchsian group, or it was a special kind of?
No, it's you can say now it's for these things. Yeah, it was just like any finite groups, because we need this thing only for these two lemmas, and actually these two lemmas used for proving this PQ patterns.
Okay.
Yeah. Okay. So actually, when I write this lemma in the slide, I actually didn't notice that these are the case of when the GCD of P and Q will equal to 1. So I actually I didn't didn't add the slides for this thing, because then it will be too lengthy. So I just write the things of that PQ that the GC of PQ greater than 1. Okay. And for our main
Are
result,
you saying that you are going to discuss the proof of existence theorem only for GCD PQ greater than 1?
yeah, actually I'm not discussing the whole proof. I add some few steps towards the proof, you can say.
But for the GCD PQ greater than 1, not for equal to 1. That's what you are saying.
Yeah, for GCD greater than 1.
Okay.
Yeah. So for okay. So this is important theorem because suppose, yeah, I am just saying, okay, fine. So how we can construct the PQ patterns? So we insert a vertex in any edge E. Then the face has the edge number of the face will increase by 2, and if the whole edge is not belonging to one face, then two face has increased the edge number by 1. Okay. The another thing, inserted edge in any face. If we insert any edge in face, then the number of edge is increased by 2. And sorry, is that any question or something?
No, nothing. Go ahead.
Okay. So so for another thing is cross cap. You just think about the, like, for the surface, you just cut the connect the RP2 thing for any polygon, then you can get this cross cap thing. So the edge number will increase by 2, and the valence of V will be increased by 2. Okay. So actually I just mentioned some few lemma to prove the PQ, and I'll just discuss these two, how the construction will work on it. Okay. So so for the non-unitable surfaces, actually it works with non-unitable surface if the pattern is PP. How it will work? If P is even, then we can just consider a P-gon and identify the edges, like like this. Then we'll get a non-orientable VP pattern. Okay. So if P is odd, then we have to do some work. So just consider 6 3 pattern client portal. It's look like this. Okay, sorry.
Are you saying P is not equal to 3 here in the lemma?
Yeah.
Then how you are taking the 6-3 pattern?
It's no. I'm here. I'm not saying that this is PQ.
Okay.
I'm not saying this is PQ.
Yes,
And we just didn't take this 3-3.
okay.
We can take 6-3s also.
Okay.
This is also okay.
Mhm.
It is actually GCD 3. This will be present in another case, but that is okay.
Yes.
You can take it. Okay. So it will be 1, 2, 1, 2, 1, and direction will be A, B, A, C, B, C. Okay. So for this, I just insert the edge here and add the cross caps in here by P is odd, so P minus 3 is even, then it will divide by 2, and here I just add P minus 5 divided by 2. So we also take this as an edge and this as an edge. So here the edge number of edges are 1, 2, 3, and plus 2. We will count 2 because from the construction 2 divided by 3. This will be P. Again, here is 5 edges, and we will cut 5 into 2 into 2. This will be P. So here for every face we will go P by P pattern, and of course it's non-immutable because we draw the 6-3 pattern in client bottle. Actually, this is the client bottle, and if we identify this all of thing, it will be like 6-3. Okay. Okay, so I just okay. So another thing, another construction is this. So how we construct it? Like the same way. I just think. Okay, I just draw again. A 2 1 2 1 2 1. B C B and A. Okay. So for this case, if it is if 2 equals to k equals to 2, then we'll get this 6-3, and this is exist because we just used it before this client board 60 and client board. So that is okay. If it is not equals to 2, then we just add insert 2 vertex in here and here, and add and insert an edge, and again we take we insert 2 minus k vertices in it, and add an edge of it. Here in the short k, and here is k minus 1. And add every edge, we add the insert the cross cap. So in every part, from here in here, the number of edges will be 2 minus k, because we just part these edges by 2 minus k plus 1, because yeah. And for cross cap and insert edge, we just get 2k and plus 2k, and 1 2 3 3. This is 6 3. Similarly, we can do this in here, and we also got this. And actually, it is 3. It will happen in 3 points. In this one, and this one. Okay. So we'll get this type of pattern. Oh, sorry. Hello. Yeah.
Nothing.
Okay. So so for two 3k, if k is odd, sorry, in this case, if we have to consider the number of minimal, actually this denotes the number of minimal faces, and for minimal faces we will get minimal vertices. We just consider this x1 at xk be k gons, which arranged like this. X has exactly one edge in common with xi minus y. So so this all collection will be like a closed disk with number of edges on the boundary. Okay. So if we just and we okay, and kp is even, so this is also even. So we just identify the edges like from the previous case. We just in this order, then we'll get a non-orientable surface which have one vertex, and the valence of every vertex is kp. So like that we will get pkp pattern. Okay. So these are the few steps how the construction will work in this lemmas. So now the generalization thing, geometrization thing, that we consider the dig group, and after that, and of course for this group, dig group is obviously Fuchsian. So this summation will be positive, and okay. So here the mi can also be 1, can also be any positive integer, including the 1. So and there is a definition for allowable. Allowable is say if the m1 m2 .mr is allowable if at least 2 entries are greater than 1. At least 2 entries greater, okay. And if 2 entries are greater than 1, then it two are equal, because it's come from the presentation of the here. They have to be same order, and they have to be the same order. Okay. So it's the natural thing. So here the any tessellation of on a surface M is equivalent to a geometric tessellation. So here the meaning of geometric tessellation is come from the definition that provides it's more general, in more general case, that that for the test, what is the tessellation in M? Tessellation in M is we have to just consider a graph K such that M minus K have infinite simply connected components, and the number of edges will be the multiplicity of edge is 2 if the edge is fully lies in one face, and multiplicity of edge is 1 if the edge is lies between two faces. So it comes from the definition. Okay. So the here the summary. Okay. Okay. I have to tell something other things. So previously we see the what is the conditions for the VR and MIs that are equal to 2MI 2E and 2MI VI equals to R. Okay, and V equals to 2I, which is R by 2MI. Okay, so the characteristics of M, which is R by 2 okay. Actually it says something like that the R will be 2 into the index of the torsion-free torsion-free group, okay, which is N. So the summary will be, if the D group is this type, then it has torsion-free subgroup of index N if the tessellation of a closed and oriented surface in M with 2N regions. Okay, and actually this is very important thing to prove our main result. So back to the proof. Okay. Back to the proof. Back to the actually the necessary conditions are more algebraic things, that the gamma be a group, and G be a torsion-free subgroup of finite index N, then the lambda, which is LCM of all M2 MIs, which are usual thing, then lambda divides N. Another thing that if gamma has odd type, then 2 lambda will divide the gamma. and it's finitely generic Fuchsian group. Oh, sorry, divides the finite index n. Sorry, is that okay? Or
Okay.
yeah, okay.
बोलो ना.
So
2 lambda
Hello?
divides just n or something else you are saying there. Here you write 2 lambda divides the index of every torsion-free subgroup. Means are you saying
yeah,
just n?
every torsion-free subgroup of Fuchsian groups.
Okay.
Finitely generic Fuchsian group.
Okay.
If it is a odd type, otherwise it is even type, then then gamma will then from the previous proposition that gamma will divide them. Okay. So for the for the converse part, we need the previous the previous summary. So we have to just prove the D group with 3 generators. Actually, it's enough because we just want to prove for triangle groups. So yeah, so we just rewrite the same summary thing again, and this theorem is proved like that way. If any allowable type of PQR, there is a PQR tessellation on a closed oriented surface like R, which is 2 lambda, where lambda is the LCM of PQR, and if it is 0, then it's 2 lambda. Then it's event type, or lambda epsilon is 1, then this is odd type. And here we can see this, that if gamma is a triangle group of PQR, then it has torsion-free subgroup or finite index, and if n divides 2 lambda, then if divide 2 lambda, and if the gamma has event time, then then epsilon is 0, and gamma is odd time, then epsilon is 1. This is our main. Okay. So
Is that in?
what?
Is it in?
Yeah. Actually, this is our main thing, right?
Okay. Maybe you work a little on this slide and reduce the wording and
I just
some
here.
pictures actually by your hand drawings or by some way, because you just
I couldn't understand. What? Say again.
Explanation in pictorial way, some of the theorems, some of the definitions.
Okay.
And then improve the slide, then we can post it on web page and we can talk other time. We, in our small group of 2-3 people, you can present sometime later. I think you are still studying this paper, right?
Actually, yeah. Some of proof. Actually, I'm seeing this right now. So you want to add more. You want to add more. I have to add more slides with good pictorial view.
With explaining the theorems.
Okay. Which I'm saying, like.
I mean, it will be helpful for your understanding itself and for ourselves also.
Okay. Okay.
Have you? I think
working.
mixed the both papers, right, in this slide?
Yeah. Actually, I compiled these 2 papers.
There are many theorems, I think you included.
Yeah. That I know,
There would
but
have been only 1 or 2
if,
theorems, and rest you would have been telling like a story. And then, okay. Anyway, so I will be in touch with you, and you can ask and discuss with me these papers. And
Okay,
you
okay.
finished little early, 10 minutes. So I was about to interrupt you earlier.
Yeah,
It was slow.
I'm
So you presented a lot of material, but in a less, just 50 minutes. So anyway, so we will discuss and we will keep talking this thing again and again.
okay, okay, fine. It's okay.
Okay, so we will be discharging now. Okay.
Okay.
Thanks. Krishnendu?
Hello. One more thing.
Hmm.
One more thing. In this. Okay. Wait. Actually, in here that there actually I'm a bit confused. The read about the R equals to 2n. Is that for is that coming from this? Okay. Why I wrote this all of thing. Okay. Is that coming from here?
What?
Actually, what?
What coming from here?
This R equals to 2n.
Go back again there.
Yeah.
Yeah, you have written there R is equal to 2n here, na? So index is something. What is?
A is index of gamma by c.
So this after this chi-m you have below written here.
Yeah.
Na?
Yeah. Actually, it's characteristics. So it is just like you can say.
The bracket thing, that box thing, I think it is related to what is called the Riemann Horowitz formula or somewhat enough.
Yeah. Something like so.
Okay, we will discuss later.
Yeah. Fine.
Thanks.
Fine.
Bye.
Bye.